Today, in this video, we are going to perform a full goodness of fit test. And this is my third time recording the same stinking video because I keep messing up, fumbling over my words. So hopefully third time's the charm and you get to see perfection. Okay, so let's take a look at 11.2. So we have this formula and it says chi, so this is a chi-squared goodness of fit test. We have chi, which is kind of like a curvy x, I guess you could say. So it's not x squared, but it's chi squared, equals the sum. It's a kind of a tiny capital sigma, but Google Docs, only goes so far. So that was the biggest sigma I could find. But that just means we're going to add up all of the O minus E squared over E. What does that mean? Okay, so O is the observed frequency. That's from the data. So that's going to be all over the place. There's nothing necessarily consistent about it. E is expected frequency from the theory. So this kind of mirrors what you've seen in the past two projects, where we had our theoretical probability, what we expected to see, versus our raw data, which is what we observed. And then finally, we're going to talk about K. K is the number of data cells or categories that we have. And K is not huge, but you will start seeing degrees of freedom popping up. So also I want to say, I had to wait a couple days between the last video and this one because I messed up so many times that I was getting frustrated. So if I repeat myself from the last video, that's all that's happening. It's just been a few days. Okay, so K is leading us to the degrees of freedom, which the degrees of freedom, the formula is going to be K minus 1. We've seen it before where the degrees of freedom was N minus 1, the total number of things. Well, for the chi-squared goodness of fit test, it is K minus 1. Okay, so number 1, it says manufacturers are testing a die to make sure that it is fair, meaning it has uniform distribution, so all of the sides appear equally, in theory. They roll the die 48 times and record the outcomes in the table below. Find the test statistic, which is what we are going to calculate with this formula, for the chi-squared goodness of fit test. Okay, so first we see that it is blank in the expected, because I wanted to talk about how that comes to be. So there's 1, 2, 3, 4, 5, 6 different categories. So for this problem, before we even start, we'll just say the degrees of freedom. Is going to be K minus 1, 6 minus 1, which equals 5. I don't want to look like a subtraction. So the degrees of freedom, there's 6 categories, minus 1, the degrees of freedom is 5. You will see this on the calculator towards the end of the video. Again, it's just something to be aware of. It's going to pop back up in chapter 13, and it's going to be more relevant then. But I just want to kind of get this vocabulary familiar with you, so that way it's just one more thing you know for the future. Okay, so if we have, we're rolling a die 48 times, 6-sided die, we would expect that each outcome has an equal amount of chances of showing up. So out of 48 times, I would expect to have 8 ones, because 48 divided by 6 is 8. And I would expect to have 8 twos, and 8 threes, and 8 fours. You see the pattern here? 48 divided by 6 is 8, so I would expect each of the 6 numbers to show up 8 times. They don't always, like you can see the 5 showed up 8 times, but the 3 only showed up 7 times. But then the 4 showed up 11 times. So is 11 too many? Does that mean it's not fair, or did that just happen because, real life data is kind of messy sometimes? That's what we're trying to figure out. So first we are going to do O minus E. Oops, not 3, E. So I'm just going to subtract 7. I'll write out the first one. 7 minus 8, observed minus expected, is negative 1. By 7 minus 8. Next one, I'm not going to write them all out. I'll just write the answer. 6 minus 8 is negative 2. 7 minus 8 again is negative 1. 11 minus 8 is positive 3, 8 minus 8 is 0, and 9 minus 8 is 1. Okay, It's kind of backwards because the observed is on the bottom and the expected is on the top, but I am here to tell you that it's not even going to matter. And when we do this next one, I'm just dividing it so my lines don't, so I can try to stay nice and neat. When we do this next one, we're squaring. So this is going to be O minus E squared. And what that means is going to become positive. -1 times -1 is +1. Okay, I get it. My phone. Mute my phone. -1 times -1 is +1. So it didn't matter if you said 1 times 1. Sorry, I'm distracted. Mute. It doesn't matter if you do 1 times 1 or -1 times 1. -1 times -1. The answer is still +1. So if you said the answer to 8 minus 7 was 1 instead, you would still get the same answer right here. All right, so then we have -2 times -2, always positive, always positive. This one's 3 times 3, positive, 0 times 0, 1 times 1. And so we have all of our O minus E's. And then what we're going to do is we're going to square them. Oh, no, we just squared them. We're going to divide by E, and then we are going to square them. So this first one, let me just write what we're doing. Divide by E, just so you know where these things, we're going to get lots of fractions here, and I'm kind of taking up giant spaces here. So 1 divided by 8, I'm just going to write it as a fraction, and I'm not even going to worry about reducing it because the calculator will take care of that. So then we have 4 divided by 8. I'm just writing them out. I don't really care what each individual fraction equals as a decimal. I can get to that at the end. So I'm just writing each number divided by 8, 1 divided by 8. And the last step would be to add everything. That's what the sigma means. Okay, so let us go to our calculator. What in the... Sometimes Zoom gets in the way of my controls. Okay, so we have just a fraction addition thing. So I'm going to go over here and I'm going to do 1/8. And remember the blinker's down by the 8, so I have to hit over before I hit plus. 4 divided by 8 over plus 1 divided by 8. 1 divided by 8 over 3 divided by 8, 0 divided by 8, I know that's 0, so I'll just write 0, and 1 divided by 8, and I get a final answer of 1.25. So I will just put that right down here. That is my test statistic. Oops, put a little final, yes, final answer is right here, 1.28. 1.25. Okay, I want to show you a quicker way to, oh my gosh, get out of here, circles. Too many. Oh, now I got rid of my lines. Okay, do you see why this is my third time making this video? Because these stinking things were driving me crazy and I made a mess. And okay, shortcut for people who are okay with fractions. If you're not okay with fractions, fast forward like 30 seconds. But I want to show a shortcut for people who are okay with it. Okay, here's the shortcut. See how everything's divided by 8? Well, what we could do instead of all of these fractions, just because it's tedious to write out this step, it's tedious to type in the fractions, I could just add up this middle step right here. I could just add that up. 1 plus 4, just faster. 1 plus 4 plus 1 plus 3 plus 0 plus 1. Add all those up. Now divide by 8 at the end, because it's the same thing as their common denominator is 8, and I get the same answer. So you choose whichever way you want to do it. Okay, next one. Same problem, but just maybe done a little more because I put the expected in here. But it's saying if professor is trying to determine if her students guessed on a certain multiple choice question, she expects that if they guess, the distribution would be uniform. So she's expecting to have 12 A's, and this isn't like the grade. This is like what did you get for number 1? She was expecting 12 people would say A, 12 people would say B, 12 people would say C, and 12 people would say D. Here's what actually happened. So let's find the test statistic, and it says round to 3 decimal places. So going back to the beginning, I'm going to do O minus E. Oops, move that side over. And so I have 12 minus 8. Remember, it doesn't matter which order I subtracted in because I'm going to square them. So I'm just like positive numbers. It's just faster. Just subtract them and get the positive. It's fine. Because when I square it in this step, then 4 times 4 equals 16. Negative 4 times negative 4 also equals 16. So I can just go ahead and have that positive answer. 5, ooh, these numbers look big, but I'm dividing by 12. So when I divide by E, I'm going to have, this is for my fraction people. If you like it the other way that I showed you, the shortcut, go ahead and do that instead of writing this step. But I'm going to write this step out for my fraction folk. My fraction folk meaning people that actually don't like fractions, because this will just be a faster way for you. And then 25 divided by 12. Okay, why did this hit? What am I doing? I'm dividing, this is terrible. Why, what? I did these backwards. This should be 16 divided by 12. Because it is our sum, our square divided by 12. This one they should all be divided by 12. What am I doing? 49 divided by 12. Well, if nothing else, you guys are using your erasers a lot. Imagine, if this is what I'm showing you, imagine the 2 videos that I did. Okay, so here we go. 16 divided by 12 plus 49 divided by 12, 16 divided by 12, 25 divided by 12. Everything should be positive. Everything should be adding. And it says round to 3 decimal places. So here is my fraction answer. And rounding to 3 decimal places, I see that the answer is 8.833. Beautiful. Final answer. And that's it. Well, that's not it, but that's it for the formula. Okay, what's the point? Well, chi-squared goodness of fit tests are just hypothesis tests with a different formula. So the test statistic here is found out by this formula as opposed to using mu and sigma or p and n and all that stuff. That's what the other formulas use. So this one is doing the observed minus the expected and whatnot. So here, starting with this one, number 3, we're going to do a whole hypothesis test. See how everything looks the same here? It's just the formula that we're going to do is going to be a little different. And of course, we have our friend, the calculator over here, that's going to help expedite that. Okay, so null and alternative, that is just write them out. Now, this one doesn't have symbols. Like the last one had like mu or p or whatever. This one doesn't. And so the null hypothesis is what we expect. So this one says sick days are a major concern. A CEO wants to determine if the manager was correct in his perception of absences. They recorded it. Okay, so what they recorded is a uniform number of absences. So this is a uniform distribution. In other words, it's all the same. And this is what you're going to see and how you're going to see it worded on the homework. So we would say the absences, that's what we're talking about here, are uniformly distributed. And in parentheses, I'm going to put all the same. That's what that means. I'm not going to write that every time, but just so you know, because we're going to start using uniformly distributed a lot. Or you could say the absences follow a uniform distribution, something along those lines. And that is always the null. The null is expected, and the alternative is what is observed. So we would say that absences are not, oops, but we're going to spell it right, are not, oh my gosh, not uniformly distributed. Okay, that's it. They either are or they aren't. They are all the same. That's like the equals from chapter 9. That's our null. They're not all the same. Remember in chapter 9, the alternative was like greater than, less than, or not equal to. That would be our alternative. Now with these chi-squared goodness of fit tests, they are all right-tailed. So I am going to draw, where's my line? This is why you don't have to worry about greater than or less than, because they are all right-tailed. Get out of here. Oh my gosh, stop it. I don't know why this PDF hates me. Okay, stay. Perfect. Voila. So now we want to draw the test statistic and the p-value. So the test statistic will go on this line, and then p-value. Well, you'll see it over the alpha. You'll see it all over here. Okay. It didn't say alpha, but when it doesn't say alpha, we are going to use 5% or 0.05. So just as a reminder, when alpha isn't given, use 5%, or in other words, 0.05. And then what are the degrees of freedom here? Well, there's 1, 2, 3 categories. There's 3 lines on this. So the degrees of freedom is 2. This is 3 minus 1. And we'll see that over here. Okay, so new test. We are going to go down to inference, because this is a hypothesis test. It's just a very specific hypothesis test. So go to inference. Oh, I already did it. Okay. Try this again. Go to inference. I don't want to give away the answer. Test, because it's a hypothesis test. And then it's like, which test is it? Well, we focus so much up here, you might not have noticed that chi-squared is written right here in words, and then the symbol chi-squared is written right there. So we are doing a chi-squared test. We are only doing goodness of fit, so we'll always pick that top line. And then I was doing a different one, so let me just clear this. And yours is probably, oh, come on, clear everything. Yours is probably empty. Okay, so observed. Now, be careful, because look at this picture versus that picture. They're flip-flopped. So it's asking for the observed first, and you're going to see it every which way. So you have to be prepared for this way, this way, this way, or this way. You never know what you're going to get. Okay, expected was all 20. And notice it knew, because I typed in 3 rows, that the degrees of freedom is 2, because it did 3 minus 1 for you. So the degrees of freedoms here. The significance level, we're just going to use 0.05 because there's no alpha given. And here we have our chi-squared, which is 0.9, and our p-value, which is 0.63. So let's see how that is interpreted on our graph. Okay, so we have our alpha right here. 5% of the graph is at 6. So this would be our alpha, and our p-value, so alpha, that's 5% right here. 5% of the graph is over here, 6 and beyond. Our p-value, it says 63%. I'll go back and make that bigger. See right here, 63.76, like if we made it a percent, 63%. I'll just say 60 to round it to make it easier, because we're just going to talk about it. But it's also written, let me make this bigger. It's also written up here, the p-value. So here is our 5% that's shaded in right here. And this is our 63%. So this is how the numbers all fit on here. Our chi-squared was 0.9. So if you look at the actual numbers on the number line, 0, 2, 4, 6, here's where 0.9 falls in. Percentage-wise, that's our p-value. That's 63%. So 63% is shaded. Our alpha is only 5% down here, because that's what we said our alpha was. So this is clearly over here in the do not reject. Okay, get that guy back. So do not reject. Wait, let me put in where my p-value is. P-value was, so here's half. So it's actually 63%, it's a little more than half. Come on, just give me an X. That is where our p the value shows up. Okay, as per usual, terrible drawing. Look at the computer graphic, it's much prettier. But we have determined because it lies on the left side, we will fail to reject, do not reject the null. Okay, so how do we write that here? It's slightly different because the wording here is different, but it starts off the same. So there is not sufficient evidence, is not, do not reject, is there's not sufficient evidence to support the claim that, and then what is the claim? So you can't get mad about this one because I did not make the rules. This is just how math is. Sometimes math and English aren't always friends. So there's going to be lots of nots in here. Do not reject means there's not sufficient evidence to support the claim. What's the claim? The absences are not uniformly distributed. Sorry, there's a lot of nots. It is what it is. I didn't make the rules. Okay, so there's not sufficient evidence to support the claim that, here, if I put it all down here, then we can see exactly where the claim is coming from. And the claim, of course, is our alternative hypothesis. Okay, so basically the same as chapter 9. The null and alternative are written a little differently. The test statistic is calculated a little differently, but other than that, it's all the same rules. So let's try this one more time. So it says training hours. Is this the same problem? Oh no, that's sick days. Okay. Training hours are essential for employees. Managers are complaining that the team was training too much, or I don't know. So the CEO wanted to see, and they surveyed the amount of training hours each employee had. So expect 50 employees felt out of their 50 employees felt they were at training for a specific number, that 30 minutes. So 50 people thought they were at training for 30. They expect 50 people to say 60, 50 people to be 90. But this is what they actually observed. 60 people were in training for 30 minutes. 54 people were in training for 60 minutes, and so forth. In other words, here's the expected, and here's the observed. That's what we're looking at. So the null and alternative. The null and the alternative. So what are we talking about? We're talking about training, employees in training. The number of employees in training is uniformly distributed. This is our expected. So I look at my expected column. What are we talking about in expected? I'm talking about the number of employees that are in training, and it's all the same, so it's all uniform. Our alternative is what we actually observed. So we just take the same sentence and we say it is not uniformly distributed. That's the difference between null and alternative. It's almost like saying equal and not equal from chapter 9, but we don't have our cool symbols like mu's and p's and stuff. So number of employees in training is uniform. The number of employees in training is not uniform. And this is how you'll see it worded on the homework. All right, degrees of freedom, let's just talk about it. I have 4 rows, so the degrees of freedom is 3. Now let's type this in to get our picture. I don't have to go back as far because these are all the same choices. These are all goodness of fit tests. There's not all the different varieties of sigma or not, Z, T, whatever. No, it's just this. So I just have to go back to this chart. Observed is first, so 60, 54, 41, and 45. Expected is all 50s. It told me my degrees of freedom is 3. I never even typed this in. I hit OK. Well, I guess I could. What would happen if I changed it? I don't know. I don't know why I would change it. So let's just pretend I didn't do that. I don't want to mess it up. Okay. Alpha. So anyways, here's my chart. Degrees of freedom just came up as 3 because that's what it is. Alpha is not listed, so it's 0.05. And I have my chi-squared is 4.4, so that's what happens when I subtract, square, and then divide by e and add them all up. 4.44, and then here's our p-value. So let's see how that fits. I'm going to draw it first, and then we'll look at it just to see if that helps you understand it better. Okay, right tail test. This is alpha. This is representing 5% of the picture, 5% over here. P-value, we're talking about almost 22%. So our P-value, if I talk about, I'm not talking about a number line, I'm talking about what percent of the picture is colored in. You know what I mean? You know how I shade. I'm not shading because it looks terrible. But here's 5%. 20% is going to be even more. 20% is like over here. So 20%. And so what I'm saying is, okay, I will draw it in. I will. Here is where my P is. And what I'm saying is, if I shade in, I'm saying this is 20%. Let me try to change the color. And then this green part is 5%. Okay, lovely, right? Let's just go to the picture. It'll be much prettier. So next, okay, so here we go. Here's our alpha. This is shaded, this hashy, you know, the little flashy things right here. This is 5% of the picture is shaded in. And right here, chi-squared is, that's where our p-value is. This orange part is almost 22% of the picture. Chi-squared on the number line is 4.44. So if I'm trying to touch the computer like you can see. So it's 2, 4, a little more than 4, 6, 8, 10. So that's where chi-squared is at 4.4. That represents almost 22% of this picture, which is way bigger than our shaded in alpha. So this is do not reject. Now, one thing I want to point out, this is, as per usual, a much better drawing. See how it's skewed? That is exactly with the tail over here to the right, skewed to the right is exactly what a goodness of fit is. We have all seen that my computer drawing skills are not exactly perfectly perfect, so that is why you're getting this. This is the most accurate, but this is what I'm hoping you still understand from what because that's what I can draw on. Okay, so again, alpha is 5%. This green part is, I'm sorry, the red part is almost 22%. So we are over here in the land of do not reject. Okay, so what do? We have our extra knotted answer. There is not sufficient evidence to support the claim. Okay, I can spell it. That, and then what is our claim? I just go up here. Isn't it so nice that I can cheat by copying and pasting? There we go. It should be lowercase t, but other than that, I like it. There is not sufficient evidence to support the claim that the alternative, which is the number of employees in training, is not uniformly distributed. I can't say that it's not uniformly distributed. I don't have enough evidence to show that. Okay, finally made it through that video. There's 2 more pages. So the next assignment you're going to see is not going, I don't know if I'm going to be on video or if I'm just going to do a quick little thing because I want you guys to practice chi-squared versus like the chapter 9 mean and proportion probability test, because that's what the whole test is on. It's like, which test is it? And then what are the steps to do it? Is it this kind of hypothesis test versus goodness of fit? So I don't know if I'll see you in the next video because I haven't decided if I'm going to make one yet, but there's all kinds of fun coming up. So I will see you at some time. Please email me if you have any questions. Bye.